PhD at Scripps in oceanography, and then did a postdoc a little bit at Scripps, and then moved to Miami in 1988, and was working at Erasmus. Went through, became an associate professor at Erasmus, and in 1995 decided that it was too hot down here, and he moved up to the Bigelow Lab in Blue Bay Harbor, Maine, where he's been since as a senior research scientist. Barney was a co-PI with Howard and I on a MODIS grant that covered the MODIS work, and he worked with Howard probably since 1988, since we got here. So,
yeah. I'd first like to thank again for the invitation to come here and speak on Howard's contribution. Probably one of the most fortunate things that ever happened to me in my career in oceanography was meeting up with Howard. So today I'm going to talk to you about reading Howard's lists, backscattering, and the particulate inorganic carbon cycle in the ocean. And this is one of Howard's applied problems that he got me involved in. Since he didn't like to go to sea, I offered some help to him. The outline of what I'm going to talk about is a brief review of coccolithophores, for those of you who may not have ever heard of these things. High points in the study of coccolithophores. So I'm going to review the literature way, way back, because I believe that Howard's contributions warrant placement amongst some of these giants of the earlier work that was done. And I'll talk about his contribution to quantifying these coccolith measurements, as well as the study of PIC, particularly inorganic carbon, from space. And finally, subsequent contributions of these algorithms to our understanding of biogeochemistry and the global carbon cycle. And I'll have a few personal reflections at the very end. So these are coccolithophores. They come in very many different shapes and sizes. They're ubiquitous in the world ocean. No matter where you go, there will be about, at the least you'll find, will be about 500 of these per milliliter of seawater. And I talk here, they're kind of the oceanic dampers. And when they're in high concentrations, they discolor the water. And they're one of the most important biocalcifiers in the ocean. And they're in this class called Primdesiophyceae. And they're evolutionary, very, very young. They all went through bottlenecks during evolution through the Cretaceous-Tertiary boundary and also with the Oligocene. Basically, all the species were wiped out and then they came back again. So here are a couple others. They come in just fantastic shapes. And here's the star of the show. This one is called Aemiliania huxleyi, and we're going to talk a little bit about this name. This is the most abundant coccolithophore in the sea. And here's another one. I just love this because this is what used to be thought of as two different species, but this guy is actually one species that has two different forms of coccoliths around it. So here are some important milestones in coccolithophore research, and I'm going back to the very beginning. Thomas Henry Huxley, who is the Huxley of Aemiliania huxleyi, he was considered Darwin's bulldog. He lived from 1825 to 1895, and he was in southern England, and in the background are the White Cliffs of Dover. And this guy basically presented public lectures, one in particular which I have a copy of called On a Piece of Chalk, from about the time of the Civil War. And this guy connected the chalk sediments to millions of settling calcareous organisms. And he provided the geological record of the species, and he also talked about all the animals that were entombed by this raining dust that came down on them. And he was a strong proponent of Darwinian evolution. This is where the bulldog part came in. And really where Darwin got was a lot related to Huxley's advocations of evolution. Another name, which is very important, and also very important in the University of Miami, was Cesare Emiliani, who was considered by many to be the founder of paleoceanography. He was a micropaleontologist. He discovered or developed this time scale of marine isotope stages, and he described the ice ages of the last million years is being cyclic. He talked about Milankovitch cycles, and so looking at these long-term cycles, basically based on looking at the isotope signature of Amelia, and it revolutionized ideas about the history of the oceans and glaciations. And so this is the Emiliani of Emiliani Oxyai. So you have two of these guys that were important in the science. Another person here, and this also will relate back to Howard, is Patrick Holligan, and who in 1983 published the first observations of dense coccolithic. This is a paper in Nature, and here you see the CZCS image from 1979, in which he showed on the Western European continental shelf these very high reflectance patches, and when he went into them in a ship, here this is a fecal pellet which is just packed with these coccoliths. And really this, if you do a Google search of remote sensing of coccolithophores, it all goes back to the Holligan paper, but that wasn't possible without the CZCS. And then in the late 1980s, I started getting my hands wet in this, and we went out and looked at blooms in the Gulf of Maine. We didn't have CZCS at that time, and we had ABHRR, and we were just looking at this Holligan stuff, saying this is incredible. We saw a high reflective patch in the Gulf of Maine. We called up the Navy. They gave us $16,000 to take a very small boat out into the middle of these. This was with Charlie Inch and Steve Appleson and others. And this is where we made the first measurements of the carbon fixation of these guys. This is what we saw. This is what it looked like. I was wearing a navy blue smock there, so you can get an idea of the color of that water. And then Holligan was on that cruise as well. There's Steve Appleson, and you can again see this bright color. And that's what we found when we sampled the water. So another important paper here was Brown and Yoder, 1994. And these guys were into deriving a coccolith flag because the presence of coccoliths in the water made the measurement of chlorophyll by CZCS very suspect. And so they decided to come up with a flag, and it was binary. You either had them or you didn't. And remember the year here, this is 94, and you saw these regions where they were flagging pixels that were measured from space for looking at chlorophyll as don't believe these chlorophyll concentrations. And here's an important paper from biogeochemistry, this guy named Roger Francois, who published this in 2002, looking at the flux of calcium carbonate measured in sediment traps at 2,000 meters, and the efficiency of the biological pump. And this is something like 89 different sediment trap results from around the world, and basically he saw this very nice relationships that the higher the flux of these carbonates, the higher the efficiency of the biological carbon pump. So now we're looking at the impact of coccoliths and other calcifiers on how fast carbon is being sequestered in the ocean. Mind you, if you didn't have this biological carbon pump, the PCO2 concentration, the CO2 concentration in the atmosphere would be about 200 ppm higher. So where does Howard fit in to the study of coccolithophores? This paper, now remember, Brown and Yoder was in 1994. This was a paper in 1988 called the Semi-Analytical Radiance Model of Ocean Color. And it had Otis on there, Bob, Jim Brown, Ray Smith, Karen Baker, Dennis Clark. And basically, buried in this paper was the basics of a two-band coccolith algorithm. Two bands, water-leading radiance in the blue and in the green, and they derived a lookup table, which are here are isoplex. The horizontal isoplex are coccolith concentration, and the more vertical isoplex are pigments. The problem is, to convert this to micrograms of PIC, you needed to know something about the optical properties, actually empirical measurements of coccoliths. And since Howard didn't want to go to sea, this was a way that we could help. So comes in 1991. These are AVHRR images of the biggest coccolithomorph feature we had ever seen. It's about 500,000 square kilometers, and there's Iceland right there, and it went from the Faroe Islands, actually past where this was 24 west, and went over to about 25 or 26 west. And these are a series of images, and on a cruise with Patrick Holligan, Chuck Trees, me, Phil Boyd, if you know that name, was on that trip. And we basically cut a line through this feature right here, and it was an unmitigated blast. And Howard sent along, oh, it is 500,000 square kilometers, Howard sent along with me a very advanced device at the time called the Rice Phoenix Light Scattering Photometer. And this instrument, which had it had a mercury lamp, and you could vary the angles that it was looking at, but this basically, I mean, I don't know, this probably is sitting in some basement.
It's in my lab. Someone would like one.
And it weighed a ton. And, but we were able to make the first measurements of the volume scattering of a dense suspension of coccoliths in the lab. And, that was a very important instrument in my career. And here's Chuck Trees. Now Chuck here was wearing a sweatshirt which was my color chip. Same sweatshirt here, he's outside the bloom, and here he's inside of the bloom. Again, you can see this bright water. And Jim Aiken, I recognize in that picture. There's Patrick Holligan, and I don't remember this gentleman except his nickname was Tiny. And then Howard came up with a paper in GRL 2001, in which there was a 3-band algorithm, which was in the red and the near infrared instead of being in the blue and the green, which had its own issues. This one had great advantages because the absorption coefficient of water is so high there. The added phytoplankton and CDOM really made a negligible difference. The bands were less likely to saturate, and there was less extrapolation for atmospheric correction. And here was the proof in the pudding here of how well that algorithm did. So how well did these algorithms work? We went out in search of coccolithophores on these Atlantic meridional transect cruises, long trips. And we've done about 10 of these. And if you look at the average relationships here between ship and satellite-derived PIC, not bad, down to a certain level, below which the scattering of the calcite at very low levels simply is not enough to make it measurable, to really see any correlation there. But up here, it really looks very good. And so that's really the basis as we've modified this algorithm over time. We've been looking at the variability in the coefficients. You can look at how these measurements vary between MODIS and CWIFs here. And you could actually start doing some oceanography by looking at distribution functions here, the concentration of calcite here. You can see the contribution of the subtropical gyres here for the 2 satellites. And you can then see the subpolar peaks here associated with these. And this is the frequency, the numbers of pixels. And then these very high concentrations out here are the blooms, these summer blooms. And then after looking at, really with MODIS Aqua and CWIFs, I'd say, we started seeing features in the Southern Ocean that really caught our attention. And it wasn't as though it was one year. Every year we saw these bright, this is the PIC product, every year we saw these bright features down there. And people started saying, well, they're bubbles because it's so stormy down there. This high reflectance, high index of refraction with bubbles, you get the same thing. And indeed, it is very stormy down there. But we started focusing on this region. And you can see for the entire aqua mission here, from the December through March time frame, you see it's there every year. And it's about 16% of the global ocean. It is an enormous feature. These are not necessarily bright blooms, but they are nonetheless highly significant. And there are even some questions that we could use scatterometry looking at current velocities in the distribution of these blooms. These are current velocities measured from space, and you see the redder it is, the higher the speed of the current. And if you super here's the same image here, and you put in the concentration of PIC versus the mean current velocity, you see that these high patches are associated with frontal boundaries where the currents are highest, and in fact, remarkably so. And when you go into these blooms, just as I showed you with the picture of chuck trees, you get this turquoise color of the water here using the stanchion of the Ravel for that navy blue color. You can get an idea of how turquoise they were. And we did a little experiment on the Ravel. We closed up the hangar, and they have a moon pool. And we decided to see if you have no surface incoming light, how much backscattered light you can see. And this was basically dark overhead, and you can see how bright the scattering is that was coming right through the moon pool. And here's our satellite radiometer descending by about 1.5 meters. So what did we learn about the biogeochemistry of these organisms from Howard's algorithms? And there are some big things, actually. First of all, here's a Patagonian shelf bloom. This is a trip we did in 2008, maybe. And basically, we did radiator patterns through this thing. Those are the Falkland Islands. This is the light scattering due to calcium carbonate. We do this acid labile backscattering measurement. We make the scattering measurement, dissolve the cocculus, and make it again. But over here, the color of these dots represents the surface PCO2. And when you calcify, when coccolithophores calcify, the stoichiometry is such that they take two bicarbonates and they produce one molecule of calcium carbonate and one molecule of CO2. So you would expect then in a coccolithophore bloom that the PCO2 concentrations would go up. And so when you run through the center of this feature, we're up to about 450 microatmospheres, and around the region of the most intense bloom, it was definitely a CO2 source. Now I'm going to focus you in on a region down here around Crozet. This image, is the 2002 to 2013 climatology for PIC. And there are features here. There's a lot of variability here. When you look at all the years, and that variability is very consistent. And there are these light and dark regions. And this is around the island called Crozet, a French protectorate, and that's called Kerguelen. So we had a cruise to visit those. And again, we measured PCO2 going down in here. And so the dots here go from about 300 microatmospheres up to 450. And the blue dots, as we come in the subtropics, you see we get into it here, and the PCO2 goes up. As we go into Crozet, it goes way up, and then as we're crossing through this traditionally dark level here, it becomes a carbon sink again. As we cross the Kerguelen, it goes up again. And the only place here it's not always uniquely that way. This is a little bit anomalous here. But Heard Island, here's another example right here, and then when we cross this traditionally dark area, it becomes a CO2 sink again. So now we're talking about global patterns of CO2 in the surface ocean, which is in equilibrium with the atmosphere. If you look at sections this is the work that we've done for 2 cruises between Punta Negra, Chile, and Fremantle, Australia, and each of these are sections. You'll note, the first thing you note was sections of cocculus, and this is depth, that the Atlantic has way more than the Indian sector here. And we're meandering, we're crisscrossing the Great Calcite Belt, which is what we've come to know of it as. But every time we go in it, we see these high concentrations of cocculus. These are the plated cells, which correspond with those cocculus in the water. And so these are really the first cruises that have verified what the PIC algorithm has seen from space, that indeed this is calcium carbonate of these coccolithic pools. So since then we've done a number of cruises, and this is where I come up with a value of somewhere around the fewest numbers of coccoliths we've ever seen are about 100 to 300 per milliliter in seawater, and in these regions down here we're in the tens to hundreds of thousands of these very small 2-micron calcium carbonate plates that are acting like little mirrors reflecting light. Even in the Arctic, now under the ice, we have found these, and so that's another story. And there are things that numbers that Howard needed to make his algorithm work, which is this backscattering cross-section of coccoliths. How much light is scattered per unit of calcium carbonate? It's sort of like how much the absorption cross-section of phytoplankton, how much light is absorbed per unit chlorophyll. This is how much light is scattered per unit PIC. And there's a lot of variability here. And one of the things that still remains to be done is figuring out how that value varies and why, so that we can do better measurements from space. We're now looking at we're now using Aquarius data for sea surface salinity, temperature data from MODIS to generate the surface density field here. And here's the PIC global image. And when you look at the gradients in density here, and you look at those same gradients for the coccolith distribution, you can see that these things are hanging out along the subtropical front, the subantarctic front, and so forth. You can even do density, temperature, salinity plots, and these are isoplus of density, and the color is the concentration of PIC, and typically, now this is global data, you can see where the coccoliths hang out in terms of just the density field. Now another major advance, I think, for people who do biological oceanography was this paper, Gordon and McClooney, and I'm just tickled to meet Ross McClooney here in this meeting, on the depth of sunlight penetration in the sea, which, you know, as a biological oceanographer, we're trying to understand how far down the satellite sensors are seeing, and this takes us back to 1975. But what we've done is you take the surface PIC from all these cruises we've done, and you look at the integrated PIC to 100 meters. If it was uniformly distributed, it would fall along that dashed line. And if you're off the line, so you're above the line, the integral is greater than expected if it's homogeneously distributed. And if you're below the line, the integral is less. And statistically, that line is way off of 1-to-1. So coccolithophores, they are not uniformly distributed, except in certain regions here at these moderate concentrations. When they're very concentrated, the integral is less than you'd expect. And when they're very low concentrations, there's a subsurface peak, and the calcite is greater than you'd expect. And then we can now look at phenology, the blooming of plants, from space. And this is the integrated global PIC concentration in moles of PIC measured from aqua. And this is what it looks like through every year that aqua has been in space. And you say, well, where are those peaks? Those peaks are at the summer solstice in the southern hemisphere. The Great Calcite Belt is enormous, and it is basically dominating the global concentration of PIC. The trough here is at the March equinox. So that's the lowest point of calcite every year. This little shoulder here, for all of these years, is the northern hemisphere solstice. And this green line here shows the fall equinox. So there's a pattern here. We don't have enough years covered with the MODIS imagery to say if there's a net trend in PIC. But we're looking at the blooming of these calcifying plants over decadal periods. It's pretty spectacular. And then if you take all the years that MODIS has been up and you plot the global PIC, and this is in millimoles per meter square versus month, and you can see this is the summer solstice. This is January solstice. Here's the equinox. Here's the summer solstice, a long drop off, and then we're heading back up through the fall equinox to the next cycle. So, finally, what we've learned about PIC turnover in the sea from Howard's list. The average global PIC is about this much, 6 times 10 to the 12 grams of PIC. The global calcification rate is almost 2 petagrams per year. That's 10 to the 15 grams of PIC per year that's being produced. If you divide one by the other, the turnover of this stuff happens in a day. So all these calcium carbonate plates, they're not just hanging out there in the surface ocean drifting around, which most people think they are. They are being consumed by zooplankton. They're being pooped out as fecal pellets that sink down and drive the biological pump. And every day, those particles are turning over. So what's happening to it? It's sinking or dissolving. There's no indication, as I said, of a trend in global PIC yet. But we have this thing here called OA, ocean acidification, which is happening now. It's demonstrable. Fortunately for the coccolithophores, they're made of calcite instead of aragonite, different form of calcium carbonate. And they're not yet, we don't think that they're dissolving, but as the pH drops and carbonate concentrations decrease, we could have a harder time. More of what we've learned from Howard's list. The highest PIC seen globally at frontal boundaries between seawater densities, 26 to 27. The greatest global PIC standing stock is found in January and lowest in March. The global phenology, the blooming of coccolithophores, shows greatest average PIC associated with the austral summer. Boreal summer is a bit lower and lowest at the equinoxes. Future directions of Howard's list. The impact of wind speed on coccolithophore standing stock. There's Ekman pumping that's happening along these fronts, pulling up deeper nutrient-rich water. Examining the PIC turnover in different regions of the world is the foci for ballasting of sinking particulate organic carbon. And are there long-term negative trends in PIC associated with ocean acidification, especially in the polar provinces where OA will have the biggest effects? Now, I'd like to end with just a couple of personal reflections. Howard is always advancing the science. Watching this over the years, and he and Ken had a weekly seminar series between physics and Erasmus. And I guess I was saying to Otis Brown last night, when I arrived at Erasmus, I was surprised that there weren't more people that are interacting with the physical oceanographers there, and also that there wasn't more interaction with physics. And this seminar series taught me immensely, and I went and I found them, still have the notes. Here is Howard's lecture from 10/25/89. And, but it was this great getting together of the biological types and the biooptics types and the physical types to talk about this new field. So Howard science has always advanced the field. This is a picture from a US-Japanese conference in Hawaii. And you'll notice there's Howard up there, sort of ceremoniously standing at the top of the mountain. And there's Dennis Clark and Jimmy Yoder, Janet Campbell, Otis, some guy here, Mark Abbott. I believe that's Marlon Lewis right there. Yeah. Program manager Marlon Lewis, Wayne Assayas, and others. And Ray Smith, of course, right there. Yeah. So Howard was at the pinnacle of this mountain, and I thought that was very appropriate for this picture. He always was bringing the community together. This is in a very emotional moment in the Oceans from Space meeting in 1990. And here he is bringing countries together. And so he basically set the stage for the 2-band algorithm. This 2001 paper set the stage for the 3-band algorithm. Gordon and Dew, that's another paper I really don't have time to talk about, but I'm hoping that other speakers might talk about that. And then Gordon and McClooney set the stage for how deep satellites see from space. And basically, he's shown that 20 to 95% of the backscattered light in the ocean is coming from particularly inorganic carbon. The largest feature in the global ocean is this gray calcite belt, defining the phenology, setting the stage for the impact of ocean acidification on these fragile organisms. And I'm going to quit there and take any questions. Thank you.
So any questions for Barney?
I have one question and I have one comment. I'll make the comment first. The comment is, I don't think NASA ever awarded a 10-year contract again. I'm sure they learned their lesson. And the other comment about that is, I don't think it's wise for anyone to accept a 10-year contract. Because your career is 30 years. And you write a proposal that's going to define the next 30-year career. That's really ridiculous.
It actually extended for
Yeah.
too long.
15 years, right? The question, say, in the intense rooms, PCO2 goes up.
Yeah.
But wouldn't that tend to dissolve the...
It's not going up high enough.
It's not up.
Yeah. And that's a short time scale response. The work we've done down there suggests that it's also tied up in nutrient balances and trace metal balances. Basically, wherever the diatoms can't grow, so if there's any silicate in the water, the diatoms can outcompete the coccolithophores and will keep them suppressed. And trace metals, we only see high values here where trace metal concentrations, iron in particular, is high enough that the coccolithophores can be happy. But silicate has to be low. So it's tied up, I'm looking up to Frank Malero up there because it's integrally tied up with the chemistry, the nutrient cycles, and the currents.
Have you made any calculations at all how much ocean acidification will reduce the backscattering and therefore increase the temperature of the ocean?
Yeah, so we wrote a paper, it was in Oceanography a couple of years ago. It would, if you took out the scattering from coccoliths, so coccoliths in the water are shoaling the euphotic zone, in effect, creating multiple scattering. So you shoal the euphotic zone and you shadow, essentially put the organisms in the deep chlorophyll maximum at lower light intensities. So it's a difference. So the question was, what would it do to the rise, the vertical diffusion of nitrate up in further? Because if you shadow the deep chlorophyll max, there's no light, they can't grow, they don't take up nutrients. It's about a couple of meters. You'd see the nitric line shoal by a meter or two. And if you dissolved it, so that's what would happen if you dissolved all those. But the saturation state of calcium carbonate, of calcite, is still in the surface waters 2 to 3. And so that's 3 times the saturation that you'd need to, before you'd see dissolution. So when it's 1, basically it's in equilibrium, and when it's less than 1, things are dissolved. The coccolithophores are not having this big an issue as the coral reefs, for example, and the pteropods that make aragonite that are subject to which is more easily dissolved.
Maybe one more question. Ken?
Yeah, I'd like to comment about the Brown and Gordon paper looking at the index of refraction of particles in the Sargasso Sea. And they inferred that you had to have something like Saharan dust coming in order to make that happen. And since the satellite era, we've seen these big dust plumes from Asia and from the Sahara, providing iron and other nutrients, and perhaps affecting the species that are found in certain areas.
Yeah, so there's also the question of the scattering of that dust, scattering contribution. So the way we measure it is we make a scattering measurement, and then we drop the pH below the dissociation point for calcite. So, and then we measure it again to look at the difference. And so there, certainly in the Sargasso, there is still plenty of calcium carbonate, and there's much less organic matter. And yes, there are ties with the trace metal fluxes that are coming in. Certainly what we're seeing in the
Okay.